All right, so this is the part 6 of our presentation, and here we're going to focus on these topics. So I'm going to talk about DSEM specific output options and plots that we've developed, and then we're going to talk about some, and here I'll be doing some demonstrations here with my laptop running Mplus. Then subject-specific variances, that's going to be another topic that we'll talk about. And evenly spaced and individual-specific types of observations. We also talk about two-level dynamic autoregressive factor score and white noise factor score models. I'll just show you some simulations. Then we're going to dive into the TWEM framework issues, time-varying effect models. And finally, the final topic will be three-level AR1 models, where we talk about within-day versus between-day autoregressive modeling. Oops. So here's a list of the DSEM-specific output options. So we have the residual output option, and that will give you model-estimated means and variances and autocorrelations for the observed variables. It's just a little misnomer that we put it in the residual output option. It's because we don't really actually produce residual. It's just a model estimated means, and this will this can be used, when you don't have type equals random, when none of the random effects, when you don't have any random slopes. When you have type equals random and you have random slopes, random loadings, and etc., random variances. Then you can use something, a new version of that option. It's called residual with bracket cluster option. And that will give you the model estimated and cluster subject-specific means, variance, autocorrelation. So for each cluster, for each individual, we produce the model estimated quantities using the estimated random effects. TEC4 and TEC4 cluster options, they also produce the same model estimated quantities for the latent variables in the model when you have latent variables. The stand option, this is the standardization option, and standardization with the cluster in brackets option also provide standardized model estimates for these models and cluster specific standardized model estimates. All these options with the cluster in brackets also provide the average across cluster quantities for these cluster-specific estimates. So we do every cluster, and then at the end we also average the results across cluster and show you those. Those are easier to read. The cluster option is also now available not just for DSEM models, but also for non-DSEM models for type equals random. So for type equals random, before we did not have, none of these options were available. The model estimated means, standardized estimates. So now in version 8 also for regular two-level models you can use the standardized estimates that are cluster specific. Again, one thing to reinforce here is that these options, all these options actually do assume stationarity of the autoregressive part of the model, and they will be incorrect if you don't have such stationarity. And again, how do you actually test whether a model is stationary, whether a model is stationary or not? So you can basically, the simplest way to do it is, introduce the time variable and, regress your variables on the time variables, and that's a very basic thing. But you can also see it, generally you can see it in the data. When the data is non-stationary, it should go up or down, or there should be some kind of a trend in the variance in the data in your variables. Or do you have a, Ellen, I have a question for you. What is the easiest way to actually, is there an easy way to actually show that an autoregressive, that there's a trend in the data? How to verify whether, is there a easy way to test whether we have stationarity or not? Actually, we'll
that depends on what kind of stationarity.
Yeah, but the easiest way to kind of like regress any of your variables that you think that you might have a trend in the data, just to regress it on the time variable and see if that coefficient is significant and things change over time. So another option that we have implemented is the HTML clickable output. So we'll demonstrate that as well. So I'm going to start with this simple example that has just a has some of these features. So it's an AR1 example with a within level covariate and a between level covariate. So it's specified like that, and like the command here will give you the autoregressive, the ability to regress, to have an autoregressive equation. We're going to have random slope for this regression on the within level. So that's a within level covariate, and random slope for that variable, for that regression. And then we also, this is the random autoregressive parameter for y, and then we also have a random variance, so that's the random variance notation. So essentially we have these 4 random effects, and they regressed on this between level covariate. And you can see these options, the standardized with cluster, residual with cluster. F-score comparison is another option that is available in these situations. For 2-level models, actually always available now, where you basically get a simple table of all your random effects one by one, and they're kind of ranked from highest to lowest. So that option we're going to illustrate. And here's some other saved data options that I'll illustrate. So this STD distribution basically is has the posterior distribution of the standardized estimates for each cluster. This is a command that will give you the factor scores. So these are the random effects. And basically that number here specifies the number of random effects, the number of draws that you're going to have in the distribution for each factor score. We actually changed something from version 7.4 to version 8 that is relevant for you to know, is that in the past we used to, when we generate the factor scores, we would actually have we thin the distribution before we generate it. So we would basically, if you actually specify this in version 7.4, it would actually take 20,000 iteration, because we only take every 100 iteration to generate the posterior distribution of the factors. Now in version 8 we changed that, so we actually take every iteration. So because it will take a long time to generate that many. So we can. This is a little change that we made in version 8. And so the other command that I'll illustrate is these B parameters that basically will produce a file with all the parameters in the Bayesian estimation. So I'm going to switch now over here and kind of do some Mplus runs. So first thing, I'm going to get this. So basically, this is the Monte Carlo, and so here's the model Monte Carlo. This is where you specify the model that is going to be used to generate the data. I'm going to use only this example here just for the data generation. And then we have the model command. Usually when we do Monte Carlo simulation, we just copy over the results from the model Monte Carlo over here, and that allows you to monitor biases and things like that. So just click on this on the run button, and then it's going to produce. All we need actually is basically the saved data file. So so this is basically the HTML clickable output, and you can see it back to the input instructions. You can see where I saved the data. It's called a.dat. That's the name of the saved data. You can click with the right button here and go back. So it's all these are links in the output file. And to get actually the HTML output, you just go over here and click HTML.
Are you here? People are excited.
Oh, okay. No, I'm glad you are. Yeah. So you can see all these are clickable, and it's easier to browse through the data file this way. So what I wanted to point out here is this part, the correlation and mean squared error of the true factor values and the factor scores, which I think is a little bit unutilized. So when we estimate in the Monte Carlo, we have the true values, right, for all these random effects. So we have the three random effects, and then we have the random intercept, which is the y variable. And so we can actually directly compute inside Mplus. We compute the correlation between the true value and the model estimated value. And this is, again, this correlation is a correlation when it's the across individual, basically. So you have the row of the true values for each individual, and then we have the row of the estimated value for each individual, and then we compute the correlation between those two. And we also compute this mean squared error, which we think it's actually a key thing to, as we monitor this estimation method, actually the mean squared error is the ultimate criterion on evaluating different estimation methods, and it goes beyond what the model parameter estimates actually give you. And what I was mentioning before is that the nickel bias, if you actually deep in deeper and you actually look at the mean squared error for these autoregressive parameters rather than just look at that one single parameter on the between level, you probably find other things. And yeah, that applies to other examples. So let's see. So we got this, we run this thing, and now we can look at the data. So let's go back to this, and you can find this part of the file that's called save data information. So it looks like that, and it gives you the order of the variables in the data file a.dat. So you can open that file, and so you can kind of read. So you can see that these are basically the labels. It tells you which column. So y comes first, then it's x1, then x2, then the cluster number, then the lagged version of y1. So you can see this is y. This is the first entry for y. Then it's x1, x2. You can see that this doesn't change across cluster, right? So that's the between level variable, then the cluster number, and then this is the lagged version of the variable, and you can see this quantity over here, right? It's the same as this quantity over here, because that's just the variable that's basically with one shift yt minus 1 basically. So that's what the data looks like. I'm just gonna now show you some of these some of the output that you get when you run this data. So let's start with this file. So this is now not a Monte Carlo. I'm just going to use the same data. When you specify the name of the variables, you can, the original file had actually 5 columns, and I specify only 4 here. You can kind of, you don't need to specify the last variable. It will read them correctly. Basically, we would ignore the last column. So the y at 1 variable is not actually specified in the data here. So we're going to look at these output options, the standardized and the residual with clusters, with the cluster option. And let's run this model. It's pretty quick. When you use simulator, everything is pretty quick. So you can increase the font just by control and the scroll button. And you can see here you can quickly go to the model results section. We have on the between level all the 4 random effects and the regressed on this covariate and the intercepts and the residual variances. As you can see here, we get the standardized model results and then R-square, and then for each of the clusters we get standardized model results and R-square and so on. So we get 100 clusters here. And then we have the residual output and the residual output for each of the clusters as well. So let's go ahead and look at the standardized results. So the first thing you can see here is that on the within level, we compute these within level standardized estimates averaged over clusters. So basically, again, we compute the standardized estimates for each cluster. I'm scrolling down to now to cluster 1. So you can see here is the within levels and the standardized model results for cluster 1. And in this, in cluster 1, basically we use for each variable for x1, for example, we use the variance of x1 for that cluster. And we use the model estimated variance of y for that one cluster. So basically the this is the random slope, and it's replaced with the estimate for that cluster. So when you standardize an autoregressive parameter, because the y variable is on the left and the right hand side of the autoregressive parameter is actually the same as it doesn't change. So that's actually 0.468 is the actual estimate for the for S2. So the standardized version of the autoregressive parameter is the same as the original version. So Let's see. We can look at the autoregressive parameter here. This is the standardized. So this is basically the average of S2 across all the clusters. So it's 0.247. Right. Let's just go back for a second and look at the model results. So let me click on model results here. So the model results that corresponds to that 0.24 corresponds to, so we have to look at the mean of S2, that's the random autoregressive parameter is 0.228, but S2 is also regressed on X2. So on the mean of X2 is, we can see what the mean of X2 is over here in the summary of data. Actually, hold on, it's univariate sample statistics. So in X2 has a mean of 0.92, and back to the model results, we see that S2 on X2 is 0.2, and the mean of X2 is 0.1 approximately. So it's adds to the mean of S2 0.02, so a total of 0.24, which matches the the average of the standardized if the standardized estimate of S2. So if there was not that regression S2 on X2, then the mean of the S2 would actually should match that average standardized result for S2 that we see in the average standardized estimates. I think what I want to point out about this is actually was kind of brought up by Noemi and Ellen is the fact that you can see the standard error over here of the autoregressive parameter is 0.15. And if we go back to the standardized estimates, which is basically this autoregressive parameter, which matches essentially, except for that little regression on the covariate, it matches, and the standard error is actually much smaller, so it's 0.07, so it's about half of what that is. And the reason there is such a difference is actually because the interpretation is different. So this estimate on the standardized is just the average across the particular individual in the sample. So it doesn't, where the model estimated means is inference on the population. So you have a sample of the population. So it's an inference on the population in general. So that standard error, so it's wider. Where this standard error is just inference for this particular 100 individuals. So just keeping that in mind as you're looking at these numbers.
Show them how to get the HTML output.
Oh yeah. So the HTML output, you basically click on this Mplus menu and has HTML output option. And you can actually get both the plain text. If you click here, you get both of them. So. It's a pretty simple switch, and once you actually click on that, all your files will be in HTML format. Let's see. Next thing I wanted to show you is some of the plot options. So it's kind of a little hard to see there, but basically some of the plot options that we've implemented now. So we have a scattered plots on the within level. And you can, for example, plot each individual by each cluster. So if you click here, show values by cluster, you get one. So basically, this is y and it's plotted against its lagged version. And also in this little box, you get the correlation, which is essentially the autocorrelation in this case. And you can have these little guys up here, and you can click on these guys, and just that will let you browse through the data for different individuals, and you can construct and kind of evaluate. You can see how the autocorrelation changes there from one individual to another. You can also do. We have these time series specific plots, and you can view the data in a different way. Values plotted by time, and so you get these plots that you saw yesterday in Ben's presentation. So this is basically the time variable, and you get just one. This is the data points for one individual, and you can again use these little guys to actually browse through the data like that. You can these other two buttons here would actually switch the variables. So okay, so there's no other variable, I guess. So in this case, so that's the. But yeah, this is basically, as you can see in the menu here, is a previous variable. But you know, my example is a univariate example with one dependent variable. So let's see what else I wanted to show you. So if you click on the, on these time series specific plots, you can also look at the autocorrelation and the autocorrelation function, and that's also for each individual. So you can browse like that through the different individuals, and you have these black lines that they basically indicate the confidence interval around 0. So it's easy to. That's kind of what other software packages do on this autocorrelation stuff. But so you basically, this is an easy way to test whether an autocorrelation is significant. So if the red line actually goes outside of the black line, like in here, the first line, then that means that the autocorrelation parameter is significant, basically. So, and you can do the same stuff with the partial autocorrelation function is also here. So that's the last element of this menu. And again, the same thing, you can test easily the significance of the partial autocorrelation. Let's see, so I was going to show you this example in, in this example, actually, I wanted to show you the example where the DIC actually changes as you. So that's our example has 4 random effects, and let's look at the model fit information. So this is the PD, so it's about 320, and we have 100 clusters, and we have 4 random effects. So generally, you would expect the PD to be around 400. And because it's a simulated dataset, I know there's no correlation between the random effects. So it should have been a little closer to 400 here, since it's 4 random effects and 100 clusters. So we've got this. There's more to the number of estimated parameters. Like you have the fixed parameters, which are very small, only 12 parameters, and those, on the scale of 400, those 12 don't make a difference. And also you have the initial conditions, but the initial conditions disappear generally. You can kind of see them, but most of the time they don't actually end up in the PD because they don't affect much. So anyway, so we have, I run 200 iterations, the model conversion, everything, and but I can see that the PD is a little, suspicious. And so then I run this same example with a lot more iterations. So let's see the input instructions, and you can see I run it with this fbitter command, which is 10,000. So I fixed the number of iterations to be 10,000, and so it runs for much longer. And let's see what the model fit information is here. So as you see, the number of PD actually increased to 394, and the DIC changed, as Ellen was saying, almost the change in the DIC actually was almost changed by 100 points from 30,600 to 30,700. So, of course, this is the more reliable DIC estimate. So, just to show you, like, for a simple example where you can use this DIC. So here's another example where I run on this data set, and in here I basically drop the random variance of the example, and you can see now the model fit information. So since I dropped the random variance, I have now about 300 parameters because I have again 100 clusters and 3 random effects. So the PD is about 300. So it looks like this is converging well, and I can look at the DIC to compare the 2 models, and you can see how this is 30,000. Versus 36,000. So the difference is about 6,000, which is again what I was trying to tell Ellen earlier, is that in most cases when you actually want to test something, that you kind of, if there's enough evidence in the data, the DIC difference should be so much larger than that variation that you get from not running enough iterations, that you should not have problems in general to make the conclusion. Of course, these examples here do not have that many other issues. So all these random effects are between level random effects. So we don't have here latent variables on the within level, which are the ones that really cause the number of parameters to explode. So this is a little still much more stable than some of the other DSEM examples. So I wanted to show you some more plots over here. So that's the full example. And now we've implemented between level scatter plots. And you can now plot things like this is y average over within is essentially the individual specific means, sample means. And you can plot this against the estimated cluster mean. And you can see it looks like really good, and you can get at the top you get a correlation between the two quantities, and that way that's a clear indication that the model seemed to at least for the mean to fit them very well. Then you can also look at things like you can also look at the variances, so you can compare the sample variance for each individual, which would be this variable y variance over within, and you can compare that to the estimated cluster variance of y. And again, we get a very good fit. So there's almost no difference between the estimated and the cluster specific, and the correlation is 0.99. Now, if just for comparison, we can go back to this example. This is the example that does not have the random variance for the y. And we can look at the same plot. So look at the sample variance for each individual versus the estimated cluster variance. And you can see here it's quite a substantial that looks much worse than in this case, which is almost a straight line diagonal line here. And the correlation between the estimated and the sample quantity is 0.75. And this is what I was saying, if you need additional evidence that your model fits, you can use some of these sample statistics to match them against the model estimated statistics to evaluate the fit of your model. And I wanted to show you one more thing in this example. That's again the full example. You can plot, so there's another run that I did, which is, this run, which is basically in this run I ask for the factor score. So as I showed you earlier, so you get in this file, get all the factor score. And when you do that, you can also add this command f a score comparison. And let's look at this. I'll open the output file. Let's just look at the f-score comparison for a second to show you how that looks now. Yeah, it's this between level factor score comparison. So, and we have these three random effects, and so you get first, you get them one by one. So this is the results for factor one. And it's kind of an easy access to, all the factor scores, and they're basically ranked here by. So the first one is the highest value for S1, and then is the second highest value, and the third, and so on. If you scroll down a little further, you get the same for factor for S2, the results for the random effect S2, and so on, the results for S3, and you can also find these results for the BY, right? This is the random intercept. The BY basically is the language for the random intercept, the between part of the Y variable. So you get those factor scores as well. I wanted to show you this little plot here, which is the, I wanted to plot here the estimated cluster variance against, and when you actually get these factor scores computed as well, you can also plot the factor scores against some sample quantities. And what I wanted to see is if the, estimated cluster variance is going to show the exponential relationship between the factor score estimate for the S3, which because the residual variance of y is essentially the log of S3. So I wanted to see if this is going to be shown here in this picture. And I kind of like, for a minute, you know, I was thinking that it should be a clear exponential line, but it's not, right? It's, you can see there's kind of a little bit of a, you can see the exponential relationship, but there's no clear line. And, you know, the reason it's no clear line, of course, is because the, in this plot, we actually are looking at the total estimated cluster variance for y, and that actually reflects not just the residual variance, of course, it's part of the computation, but also has the autoregressive parameter, affects the residual variance is divided by 1 minus the autoregressive parameter, and also you have the regression on the covariate. So that's basically the total variance, and that's why it's not pure exponential relationship. But then I wanted to show you what it would look like if you didn't have those things. And so here's a little example. So the input instruction, I I don't have any autoregressive issues here, just a random variance on the within level. And let's look at the same plot. So we're looking at the S3 factor score versus the estimated cluster variance, and you can see now it's a pure exact exponential relationship. So let's see, what else did I want to show you here? The back to this little example. Oh no, actually I wanted to do this one. No, okay, this one. So you know, one thing to keep in mind that you're actually comparing some of these things is that we kind of tend to, it's a little bit of a mess right now, we tend to use different iterations in the MC estimation for different things. And so sometimes when you expect the same number to appear, it actually doesn't appear, it's not exactly the same. So for example, let's see, in the factor score comparison, I can, so the between level factor score comparison, I will look at the value for S2. This is the autoregressive parameter for cluster 1. So this cluster 1 is right here, and it's 0.62. And so I'm going to contrast these two. So that's, and remember that these are the factor score, and they are estimated after. So we have the convergence part of the model estimation, and then we actually use, you know, 200 draws after these to actually estimate this factor score. So it's 0.62, right? And now let's look at the standardized estimates for cluster 1. So for that same cluster, you can look at cluster 1, and you can see this 0.468. So it's 0.462 versus 0.468. So it's not exactly the same, right? It should have been exactly the same if we were using the same MCMC iterations, but we actually don't. So, so we just keep in mind that there's some little variation here and there, just because of the, you know, if you use a very large number of iterations to estimate both, you know, then they will be the same. But here, for the standardized estimate, what we do is actually we use the last 1,000 iterations from both chains. And so if they're not, in this case, only 200, so we use, because we didn't run even 1,000, so we just use the ones that we have. But in this 0.468 are basically the first 400 iterations from the two chains, the 200 iterations per chain, and we use that to estimate the standardized quantity, where for the other, the F comparison, we use just the last 200 iterations. So let's see, what else I wanted to show you is the...
Is there a chance you could show a piece of the code at some point?
Sure, yeah, it's right. So Bengt wants me to show a piece of the code, so here you go. Hold your hats, was it? Yeah, it's fun to look at it. I'll show you what where Bengt spent his youth. So here's all these files over here. This is what Bengt did in the 80s and 90s. All these files, it's like a lot of files. We have to work with all these files to actually keep going. where it's a long list of files. There you go, probably like 400 files there. That was the original Mplus code before I got there. And then, so, anyway, so this is the, yeah, here's the basically, these are our base files. They're not that as many, but they're very long and so really hard to read, but they're basically, yeah, so.
Can you zoom in on it?
So, yeah, can I zoom on it? Let's see if this is gonna work. It's just a nightmare, so. Yeah. Yeah, no, I don't know anything.
Tell us what you're doing at that code moment.
Oh my God! It's just so that's the Kalman is the internal code word for the DSEM. That's what we used to call it. So this is just.
So what's par free then? What's the par free line mean?
Oh, this is just the number of. These are the actual model parameters, and just yeah.
I see that they're writing it down here.
So yeah, here's this is kind of some part of the standardization because these are these are the variances for the latent factors. Anyway, it's no use. You can stay as that code as long as you want. It's no use, generally speaking. So okay.
So this is our version of open code.
Let's see. So what else? Wait, I wanted to show. Yeah, I wanted to show you some of the saved data files actually. So here. So here, let's look at these files. The saved data file, again, this is the standardized distributions. We wanted to save the entire distribution for all the standardized parameters. So this is one.dat. And you can go back to this part of the output file, which is called the save data information. Oh yeah, this is the, so here you can see how the factor scores are saved. If you haven't looked at that. So in file 2 here, so you have again the columns. So first is y, then it's x1, then the lagged version of y1, and you can see there's a star for the initial condition. So that's of course a missing value that is the auxiliary parameter, and here's the initial condition for the next cluster. And basically then you have these 5, after that is x2, which is that fourth column, and then after that you get the factor score estimates for S1. You get S1, the mean estimate for S1 in that first cluster. So that would be this column. Then you have the median estimate, and then the standard errors, and these two will be the confidence intervals. And because it's a between-level latent variable, you get those things don't change across the times. This is basically the time. At the very end, you can see that's the cluster variable. It's the last cluster variable. So that's the file with the factor scores. And then you have the Bayesian parameter estimate. So this is the file that contains all the imputed values for the parameter estimates. And here you can see this is so that's file 3. And you have, again, it starts with the chain number. So the first column is the chain 1, then it's the iteration, the MCMC iteration. And
we have a quick question, Tira.
Yeah.
Hi, Timmy. The S1, the factors are all, because it's a Bayesian estimation, it's plausible values, right?
That is, so the plausible values are not saved here. I think you need to use the factors equals all command to actually get the actual imputed values across the iterations. So this is just a summary. So that will be just a summary. Then it gets a little bit larger, right? Because if you have 200 imputed values, then you get 200 columns for. So yeah, here's that. Basically, this file 3 contains all the fixed parameter estimates, and there are 12 parameters in this model, and you get the 12 columns and chain 1, and then the MCMC iteration. And then the last file that I wanted to, oh, actually, hold on. One thing I wanted to show you here is, you know, so again, just a little understanding about what we do. The reason we actually compute the, ultimately we compute the factor score distribution after the model has converged. So we first run the model, make sure that the model is converged, and then we run additional 200 iterations, and we store the factor score from, you know, a model that's already converged. And so if you, these are the actual model parameters that you get during the estimation. So this here is, you see, it's still chain 1, and then it comes chain 2 from iteration 1 to 200. And then what happens is these quantities right here, you can see that we went back to chain 1, and then we, these are the iterations 201, and it goes down to 400. And basically the factor score are generated only from chain 1, and then you have these 200 iterations that impute those 200 values for the factor scores. And you need that part of this file. You know, we actually, this is something new in version 8 that we added, is if you want to actually compute something that involves not just random effects, but also fixed effects, so you have to actually use the same iterations. So you know, if you have to compute something that a function of the random effects and the fixed effects, you have to make sure that the quantities you're using to compute them come from the same iteration. So that's a kind of a little technicality, but technically you need those values imputed from the same iteration to compute more advanced functions.
And in terms of the factor scores, then the advantage here is that their variation, the standard error for the factor score, takes into account the uncertainty of the parameter estimates as well, which is what you should do.
That's correct, which is, yeah, which is not typically done with ML. So let's see, the last file was the last saved data file is this standardized file. So you can get the standardized parameter estimates also, and you can see that they come as a, you know, the clusters of each individual, and then chain number and iteration number, and then you get these 10 quantities, the 3 versions of standardizations that Mplus computes, as well as the R square. And yeah, you can see that file here. This is the 3.dat. No, it's 1.dat, sorry. So it's, yeah, it's pretty large file, and you have to kind of, you know, keep, so yeah, basically these are the different parameters. These are the standardized parameters for stdyx and stdy and stdy, and that's the R square. The last column is the R square, and it goes through the iterations, and the second column is the chain, and the first column is the cluster. So you get all the entire posterior distribution if you need to look at that. It's currently not in the plot. It was in the plot, but then, you know, we couldn't actually release it. It wasn't working super well, so we had to take it out before the release. But anyway, you actually have these available if you needed to do something with that. So let's see, do I have anything else here? Oh, the plausible summary, I guess I wanted to show you. It's one quick way to actually also evaluate this, you know, to evaluate the factor scores, and generally the whole estimation is to just look at this summary of plausible values. And you can see here, this is a 0.247, and that matches, you know, what we were talking about before is the mean of the autoregressive parameter. But you can see that the factor scores, the estimated factor scores, when you add them up, you know, it matches actually the model estimated quantity. And you can kind of, so these are basically summary of all the plausible values that have been estimated. Okay, I think, yeah, that's, was that my live demonstration, I think. So, yeah, well, yeah. So, anyway, I think we're going back to some real stuff. So, no more fun. Back to the formulas. Okay, so this. All right, so we are back to subject-specific variance topic. So in this paper by Jean-Lin, Laurençau, and Hamaker in 2015, they showed that subject-specific variance is actually important in DSEM framework, something that we generally actually ignore in multi-level settings. In general, multi-level models, whether this residual on the within level, the variances on the within level, whether they will be subject-specific or not, is not that important. So nothing of the structural parameters are not affected by that, whether you account for heterogeneity in the variance of the within level variances. So we tend to ignore it. We've been ignoring it so far. Now, in this paper, they actually showed that you actually can get the structural parameters to be biased unless you account for that, variance, subject-specific variance on the within level. And it's something that it's really hard. It's a very raw evidence that it's kind of hard to argue against. And so we had to actually implement. That was like, gun to the head sort of situation that we needed to implement that. And after pushing some kind of a trickology, I was trying to explain to Bengt and Ellen how they can do that already, but they decided that, it's too hard. And, we actually ended up implementing that log of the variance method. And so here's I'll just kind of introduce you a little bit to the simulation study that actually points out that there's you get biases unless you account for the subject-specific variances on the within level. So we have this simple model, AR1, two-level AR1 model with random autoregressive parameter, and we generate data using subject-specific variances. And what they show in the paper that if that is treated as a fixed parameter, so a non-random parameter, which is estimated equal across all the subjects, you can actually get biases in the mean of the autoregressive parameter. And here's a little simulation that I did, and it turns out that that bias actually is quite dependent on the covariance between the autoregressive parameter and the subject-specific variance parameter, and the higher that correlation is, the more visible the bias is. If you account for the subject-specific variance, then you get no bias and the coverage is great. And if you ignore the subject-specific variance and you just estimate an autoregressive AR1 model with subject-invariant variance, with non-random variance, then you get biases in the mean of the autoregressive parameter, you get biases in the variance of the autoregressive parameter, and the coverage is hurt as well. If the covariance between the two is none, then there's no bias. So the higher the variance becomes, the bigger the bias becomes. I wanted to actually see a little more what I was just talking about earlier for the autoregressive parameter and the nickel bias is what happens if you actually look at the mean squared error instead of just looking at the mean of the autoregressive parameter and the variance. We can actually also look in a more detailed way using the mean squared error between the estimated and the true autoregressive parameter. And it's very clear in that case. Well, you can see again that the mean squared error for accounting for the random variance is much smaller than the mean squared error when you ignore the random variance. And even more than that, the distance here is about 0.1, which is about twice the bias that you saw here, meaning that that indeed this thing happens. If you just look at the average of the autoregressive coefficient, then that's going to hide part of the problem. And if you actually look in the mean squared error, that actually will show the true error that you actually get when you ignore the subject-specific variance. Anyway, so again, when this covariance between the autoregressive parameter and the subject-specific variance parameter decreases, the difference in the mean square there also disappears. The one thing after I did that Monte Carlo simulation, then I actually did that also in two-level models. So again, in standard two-level models that are not dynamic models, you don't have that issue when you look at the structural parameters. However, if you actually look at the mean squared error as the way to judge the estimation, then you can actually see that even in standard two-level models. And the reason, this is kind of like a little bit of a myth that we don't need this in two-level models, standard two-level models. So you actually need, given that it's, now we have it implemented, it's probably a wise idea to also explore the possibility for, cluster-specific variances also in standard two-level models. And the reason this happens actually is because you extract more information from the data that's already there. So this is an additional variable. If you estimate just a two-level model, you kind of ignore the cluster-specific variances. If you add the cluster-specific variance, all of a sudden you get another variable that you have that you can use as a predictor or to correlate that variable with something else, and actually provide better estimation for all the factor scores and random effects. I tried to actually deep in deeper to show some simulations about the covariance, random covariances, and I was not able to find anything very interesting. I think for random covariances, the situation is a little, you probably need much bigger sample size to actually start seeing these kind of problems.
Just a comment on that slide, Timur, in passing. Your second bullet from the top. So that's there are examples of that in the new version 8 users guide, example 9.28 and 9.29. That is not DSEM model, but regular two-level models.
All right, so we're gonna move then to the next topic, unevenly spaced and individual specific times of observations. So the basic model, assumes that, the times of observations are time 1, 2, and so on. But that never really happens in real life. I mean, unless you have daily diary data. So in many applications, times are subject specific. So what we do is basically we slice the time in a grid, and then we place all the observations in the bins on that grid, and then we introduce missing values for those bins that don't have any observations in them. So if you have this little example from the simulation that follows, and the data looks like that. So so we have a 24-hour period. We slice the grid into 24 hours, and this subject had 5 observations in that day, and 5 different variables are measured, and in those for those hours where observations was taken, we have the row with the observation, and then everywhere else we have missing data. So here's a little simulation that kind of explores the quality of this approach, where we introduce missing data for to get this grid to get time-specific observations. So we have just a two-level factor analysis model. We have so basically it's a standard two-level DAFS model. So we have a factor on the within level that's measured by these 5 observed variables. And then we have an autoregressive AR1 model for the factor. And then on the between level, we have another factor model with a between level factor. And to introduce this kind of a missing data in this Monte Carlo simulation, right, we want this missing data to be, all the variables to be missing at the same time or not missing at the same time. And that's basically done through, so you have to specify first the missing command, so specify that these variables can be missing. And we introduce a binary indicator here that is going to make the variables be missing at the same time or not. And the model missing statement is the statement that actually tells Mplus how to generate the missing data. And it's based on a logistic regression. And here you have this, we introduce a binary variable in the model that's it's a within level binary variable that's unrelated to anything else in the model, and it's just there to for generating the missing data. And you can specify this. This is actually a probit because it's within the Bayesian framework. It's a probit threshold here, and with 20% of the time this is 0, and 80% of the time it's 1. And when u is 1, we have this logistic regression, and that refers to the threshold of the logistic regression. And when u is 1, the threshold changes from -15 to 15. And when it's -15, the variable is 1, and the variable will be 0. And when it's u is 1, then for all these variables, the threshold will be 15. And so you get all the variables to be missing when it's 15. Then that's the probability in logistic scale for the variable to be missing. So that's how you generate this kind of data that is missing at the same time or not. So here's the results of this simulation. So we vary basically the percentage of missing value in the simulation. So I explored these 4 values, and this is a fairly complicated model, the DAFS, 2-level DAFS model, AR1 model. And as you can see here, and we just an easy way to judge the quality of the estimation is through evaluating the autocorrelation, the autocovariance, the autoregressive parameter for the factor, and the true value is 0.4. And you can see as long as the number of missing values is here is 80 or 85%, I get fairly good estimates, and the coverage is fairly good as well. As I increase the amount of missing data, the quality of the estimation becomes worse. And essentially what happens is that you basically need to run extremely long MCMC chain because you have so many missing values that need to be imputed to get stable convergence that explore the entire space. You need an extremely long MCMC chain. So basically, I don't run an extremely long MCMC chain. Basically, I just look at when Mplus claims to be converged, to have converged, and if you look at these values, then they look biased, so they're biased, and the coverage is pretty bad. It's also, what happens is that the amount of computational time that's needed when the amount of missing data is so high increases quite substantially. So this is 18 minutes when it's 95%. This is 18 minutes per replication, so when it's 95% missing data. So we kind of started to feel the situation that you probably can get up to 90% missing values, but not more than that. Probably optimally would be 80% missing value. Between 80 and 90% missing values can be introduced into the data to account for uneven spaced times of observations. And the other argument is that if you include that amount of missing data in missing rows, you will probably be able to extract that level of information from the time of observation. So with introducing this kind of that amount of missing data, you can approximate fairly well the real times of the observations. And we also implemented that in the t-interval command. The t-interval command is based on this value, which I call delta here, and it's basically the segment that you want your grid to be based on, which will be either an hour or a day or a week or some kind of interval where you have one observation. That's the goal, to have one observation in that delta value. And what the algorithm essentially does is takes this is the variable that's the original time of observation, and so it divides the time of observation by this delta, and it looks at the nearest integer for that quantity and places, and that will be the new Mplus time that's going to replace the original time with this time. And obviously it's an approximation. And there's some complications if you end up with situations where 2 of these observations yield the same nearest integer. You can't have like 2 observations be taken at the same time, and so we do a little ad hoc algorithm to resolve that, and it's essentially that we kind of look for the nearest empty bin. We place the observations in these bins with the size delta, and then we look at if you have more than one observation in a bin, which would be a contradictory situation, then we look at the nearest bin that's empty. We look up or down, and we preserve the order of the observations, but we essentially scoot them over. So Mplus will actually warn you if observation is moved more than 5 bins away. So you get this kind of warning. One thing to actually kind of keep in mind is that there's two ways. If you get this kind of warnings from Mplus, then you can do two things. I guess you can look at the particular individual that is producing that warning. And one of Ben's examples, here the individual, most of the individuals in the sample had 5 observations a day, where one individual had 30 observations in 2 days. And when you try to, or 30 observations in 1 day, something like that, I don't exactly remember the, but what happens is you can't fit all these 30 observations, even if you put them in all the bins that will in the first 2 days, and eventually they have to be pushed out. So one thing you can do, which is a part of Mplus, is like instead of using all these when the observations are taken too frequently for particular individuals, and that individual is quite different from the rest of your sample, you might actually kind of come up with an ad hoc procedure that deals with those things, and perhaps not even use all the observations or average the observations that are taken too close together. But ultimately, I was thinking is that the one thing that one actually should do is ahead of the design of the collection of the data, and understand a lot of these mechanisms are to select random time points to get your subject to record their whatever you're trying to record at random time points. But it's very easy to implement as your sampling procedure that you can take random time points, but make sure that they're not less than, if you're not going to use, if you make sure that they're not less than 1 hour apart. So if they're more than 1 hour apart, then you resolve this problem. If you're going to use 1 hour as your delta, then you won't have this problem. I mean, it doesn't even make a lot of sense that you take a lot of, so you can randomize the times of observations, but it makes a lot of sense that you have instead of completely randomizing them in the design of the data collection, that you make sure that no 2 observations are actually less than 1 hour apart. And you also help Mplus in that way to make it easier for you to analyze the data later on. And again, this is just an ad hoc algorithm. It's very simple, and you can make your own algorithm to approximate your times of observations one way or another with integer values that the time series methodology, the discrete time series methodology is based on. Here's a little example that kind of shows what Mplus does, and this is basically some real continuous time points, which is basically this blue line. And what Mplus does when you say use delta equals 0.05, and then in this diagram I use delta equals 0.08, which is a little cruder scale for the time. And you can see that when you choose a smaller value, the Mplus is actually trying to approximate the real curve a little bit better, where here it's kind of not doing much. When it's a little more crude, there's a couple of observations of missing data observations, but otherwise it looks like it's just ignoring the specific times of observation. So if you actually choose a delta that's a very large value, then what Mplus will end up doing, if it's very, if it's 1,000, if you put 1,000, then basically Mplus will assume that you really want the times of observations to be considered sequential, and the distances between the observations will be completely ignored. So anyway, so the smaller delta you choose, the more missing value you're going to introduce into the data, but the more precise the computation will be in terms of matching the real times of observations. So the smaller value you choose, the more problems, the more missing data you're going to introduce, the harder the convergence. So there's a little bit of a balance that has to be taken into account. Here's another little plot I made. So here's if you use this, imagine this will be your hour, the hours, and then here's the true observation, and it's going to be basically moved over here. There's another one that's over here, will be moved again on to 4. And then here we have in between hour 5 and 6, you have 2 observations. So one of them gets to go to time point 5 and the other will go to time point 6. And if you add 3 observations here in the same hour, then we're going to be using 7 as one of the closest hours. So it's basically just moving the times of observations to this integer grid.
And these plots are being developed as we speak?
Yeah, so these plots actually will be also in Mplus 8.1. So I think they're being worked on now. Here's another little simulation that I thought that is kind of quite different and informative about the quality of this methodology in terms of dealing with subject-specific times. And it's quite different from the previous one that I showed you, because here we're actually varying the delta. So I didn't put a lot of words here, but it's in the paper, and I'll just explain how it works. So we generate, so I'll just focus on this lower part of the table here. We basically generate for each individual, so it's a 2-level AR1 model with subject-specific times. And basically what I do is I generate 1,200 observations for each individual. And then I remove 95% of them. I take them out, so those are considered missing. So we end up with 60 observations. And those 60 observations will have some integer times of observations, right? And this is using delta equals 1 is how I generate the data. But let's see what happens when you actually make a more crude data. So we'll use delta equals 2, 3, 4, 5, and 10. And so the missing data from the data generation is 95. If I use delta equals 1, which is the true delta, I get, again, of course, 95% missing data. If I choose a cruder time interval, which will be twice as what the original was, then I get less amount of missing data. And as I increase the more crude the time scale is, I get less and less missing data. And if in the first part of the table, I generate out of the 1,200, we generate 300, and we remove 80% of those to get against about 60 per person. And as I increase the delta, the delta becomes so crude here, delta 10 times the original scale, it doesn't produce any missing data. So it's all the observations are considered to be taken from observations 1 to 60. So we generate this, we have some kind of an original true time scale, and then we make, in reality, we use some kind of time scale that we think is good enough to actually represent the process. And this simulation will show you, what if you had not chosen small enough time interval to represent the process. And as you can see, this is basically the autoregressive parameter again. And if you use the true original scale, then of course the estimate is unbiased, the true value is 0.8. And even with 95% missing data, it actually got an unbiased estimate. As the scale actually gets more and more cruder here, you get less missing data, but also the point estimates actually gets more and more biased, and the coverage actually gets worse. And same thing in this part of the table. It kind of shows at 80% missing data works great, at 58% is okay, 60% of missing data in the analysis, it's still okay, but it gets progressively worse. So the conclusion of this is that, this is not a perfect methodology, it's just, it's an approximate solution. So you have to be realistic about it. And one question is, how do you actually choose the delta? You have your real data, and this, in order of importance, is what we think. So choose a scale that's natural, because you have to interpret the model. All these time series models, they change if you change the time scale. So if you work with a model that's with time interval 1 hour, that's not going to be the same model if you change the time interval to 2 hours. You actually have to make some implications about what the model will look like if it's for a 2-hour period. Even if you know the true model, it's not about anything to do with the estimation. These models, if you change the time interval, they have different implications about the models. Like, for example, the AR1 model is the easiest to deal with, but because it's just one parameter, the autoregressive parameter basically gets squared as you double the time interval. But you see the kind of models we do. They have everything, so they can get as complicated as you want. And those models that are more complicated, they're not easy to translate. So point one is choose an interval that's actually easy for you to interpret. So in Ben's example, he chose an hour, and that kind of worked fairly well. As you choose the interval, make sure that you produce a reasonable amount of missing data, because otherwise it's not going to go anywhere. So if you try not to go above 90%. And again, notice the difference here. The more complicated the models, the less missing data we're going to be able to handle. And one more observation is that in the TVEN framework, there's an additional complication that happens, is that as you produce, as you choose smaller and smaller delta, then you get more and more time intervals. And the observations in the data are going to be distributed in these many more time intervals. And then for each time interval, we're actually estimating random effects. And so this approach is even more fragile in cross-classified framework. So be aware of that. That in cross-classified modeling, you can actually you should be more aware of producing even less amount of missing data. So next topic is we move to these dynamic autoregressive factor score models and the white noise factor score models, and those these are kind of classic factor score models that have been explored in the past. They've been usually dealt with in single-level models, but now we can do them in two-level models. And just a little simulation study here. It's a DAFS model with lag 3. This is how you specify the factor analysis model with lag 3. And the DAFS model, basically you regress the factor on the previous 3-period factor values. And here you have also a between level factor analysis on the between level. And you wonder how well this can be estimated. Well, it's estimated super well. You can see it's virtually no bias anywhere. Everything is perfect. The reason is because one reason why this model is much simpler to estimate, because there's no random effects anywhere. So all these the parameters are cluster invariant, right? I did not have type equals random here, so that's a very basic model. But in these very basic models, the estimation is super straightforward. One thing to note here is that as you're choosing, and exploring various if you want to conduct simulations to see how well this works, is the autoregressive models, they have to be stationary. To actually get a stationary if you don't get a stationary autoregressive model here, your data is going to explode, basically. So, Mplus actually has a way to, to detect this, but you should basically still be aware when such a model like that is stationary. And one simple way, if it's an AR1 model, it's very simple. It's just the AR1 coefficient has to be smaller by absolute value than 1. If you have an AR3 process like that, then a simple kind of rule of thumb is that the sum of the 3 coefficients here should be less than 1. So if the sum of the autoregressive coefficients, if they're all positive and the sum is less than 1, then the process is stationary. The general condition is basically that it's that verifies the stationarity of a process involves finding the roots of a polynomial of degree L, and those have to be less than 1. Here's the white noise factor score model, and in this model, it's quite different from the DAFS model. Here, basically, the factor from the previous periods can affect the indicators directly. So here's again the factor model, and it's of lag 5. And here you can regress all these indicator variables on the factors from the previous 5 periods. And again, on the between level, we have a factor model. So how well does this work? Yeah, really well. So it's an easy model. Now, in the white noise factor score model, there's no stationarity issue. So the white noise factor score model is also always stationary, so it's easy to conduct simulations with that. And then, the inevitable happened is, Bengt said, well, which one should we use, white noise or the DAFS model? And, we kind of, this is where this is the very beginning of the Mplus development what happened. So we were struggling to figure out how to compare these models and which one we should choose in practice. And I don't know who actually tried it first, but somebody tried it first. And anyway, somebody tried it, and we realized that you can actually have, you can combine the DAFS model and the white noise factor score model into one model. So let's see how that works. You got your factor score statement here. You have the autoregressive part of the model here. But then you can still directly regress the indicator variables on the factor score from the previous period. This is another, if you think in same terms, this is another oxymoron thing that happens, right? You can't have this, generally when you have a predictor, you can only have the maximum amount of coefficients is the number of indicators you can have. You can't have more regression parameters than that. But here we have 5 indicators, but we can also regress the factor on that predictor and also each of these indicator variables. So we end up with 6 regression coefficients, even though they're 5 degrees of freedom. So then we, I had like some, of course, it's like, I always thought, I kind of had the feeling I'm going insane with this stuff. And then I wrote some formulas, figured out that it's actually not that crazy statement. It's what happens is that you have essentially a DAFS model where the factor actually has a ARMA1-1 distribution. So it has a different, so it's a DAFS factor analysis model, but it's instead of a AR1 model for the factor, it's ARMA1-1. So it's an equivalent model of that. But we kind of quickly, when we run into that, I think that's when we decided we gotta get somebody to help us. I was in Utrecht and we talked with her and she kind of explained to me how it works and why it doesn't work. And again, it's because when this analysis of the degrees of freedom is all based on our training in SEM, where you can count the number of degrees of freedom because the sample mean and sample variances, they are representative of the data, but sample mean and variances are not representative of time series data, so the same logic no longer applies. So these models are perfectly identifiable, and there's actually a paper by Peter Molinar that goes into, in 2017, that actually goes into many more other equivalent models that of these sorts. And again, this, you can see here that how well it works. It works quite well, perfect coverage, and there's no bias in any of the estimates. So next topic we will go into. I can skip something, Bengt, if you.
Could you do I think the last bullet you should save for this afternoon.
Okay.
But maybe do a partial version of TVEM, if you can.
Yeah. So let's look at some TVEM modeling. So we include in the DSEM framework, it's a general TVEM framework. So it's a multivariate, multi-level time series. We have continuous and categorical dependent variables. And we will illustrate this with this simple example. Again, I'm going to use a mirror 1 model, so the measurement error autoregressive 1, with a covariate, with time-specific mean and regression coefficient. So here's our, so it's a 2-level model. So we've got the time-specific effect, time-specific contribution to the mean, mu t, and then we've got the subject-specific contribution to the mean. And then we have a regression coefficient for our covariate, and that changes across time. So it's beta t. And then we have a factor that's measured by this single indicator, and the factor is going to have an autoregressive equation. And we're going to put some completely non-parametric functions here for these parameters. So mu t is just going to be the log of t, and beta t here is going to be a quadratic function of t. So we're just going to try and see if we can actually estimate these things using the DSEM framework, and they're completely arbitrary.
Just to remind people, TVEM means time-varying effect models. So intercept and slope are varying across time.
Yeah, but essentially any parameter, any structural parameter here could be varying across time. So the way I like to think about this, and it kind of Bengt I think was giving this yesterday, but I think it's such a new concept. It's always good to hear it twice and maybe several times. But there's three models essentially that we kind of separate. Three models here that you can estimate. So the first one I call is non-parametric, the second one is semi-parametric, and the full one is full parametric. And the first one we sort of call as the exploratory FEM DSEM. So we do not assume any parametric shape, no parametric shape is included in the model. We simply estimate this as completely, normally is distributed random effects. Now, in the generation of the data, we use 500 individuals observed for 50 time points. So those effects essentially are estimated with we have 500 observations at each time point. So those will be easy to estimate, of course. It's a toy example, but just to illustrate what it can do. The next type of FEM model is a semi-parametric cross-classified model. So you can add a shape to those time-specific random effects. You can add some kind of a parametric shape, but you can still have those still can be random effects. So they can have a time-specific random effect that will allow to fit it to the particular time point perfectly. And then the last one is when you actually remove the time-specific, the actual random effect for each time. So you leave just the parametric part of these parameters. And because you don't have, no longer have time-specific random effects, then you can actually use two-level DSEM to estimate those models rather than cross-classified, which is, of course, easier to estimate. And so I'll just give you a little examples of how to do all these three models here. So again, you say type equals cross random here to actually use the three different levels now with the full generality of the model. So we have the within model, between time, so that's the time specific effects, that's the intercept random effect, and that's the slope for the regression parameter. And we have the subject-specific individual effect here. That was, I'm estimating the mode that I used to generate the data. Again, here we have the autoregressive equation for that factor that's measured by the single indicator variable, as usual on the within level. And we can use these commands here to get the factor scores for the time-specific random effects. And we can plot this against the true values. And this is the intercept, the blue line is the intercept true values, right? That was the log of t. And these are basically the estimated values that Mplus provides. And you can see this is a perfect fit. So here's the slope for the y on x regression. And we generate that from a quadratic function, and this is what Mplus will end up doing. Is actually because they are subject-specific. Remember, these are time-specific random effects, so there will be somewhat. We estimate this a little bit of a noise in there, and that's why it kind of looks like this. And now we're going to look at the next model, which is the semi-parametric, which now we cannot, once you actually see these curves, and that's what Bengt did yesterday, right? That's exactly what Bengt did yesterday. He estimated the exploratory version where he assumed no shape in the random effects, which is basically just estimating them like this, just as two separate random effects, completely unmodeled. And then once you actually see the shapes, which is obviously you can see the quadratic here, and you can see the logarithmic here. So then we can actually construct these predictors in terms of time. So this is basically I kind of scale them here so that they get good coefficients. The coefficients will be 1 and -1 in the estimation, so we don't get into small values. But so we add these parametric shapes. And so the intercept is regressed on the log of t, and the true value of this coefficient is 1, essentially. And also we regress the slope of y on x on the quadratic, the linear term on a quadratic term in terms of the time. And so now you can see this. Now we have these parametric shapes included in the model, but we still are going to have these residuals estimated for this for y and s, and those residuals are actually 0. The true value is actually that they're 0. And so we do the same curves. Actually, so this is no. So the same. We can actually do the same curves, and you can see again that the intercept is matched very well. But look what happened to the slope. Now the slope is much better than it was before, right? That was the picture over here. So it helps when you add a parametric shape for the curve. So and then here is finally it's the final model, which is basically just to once you see that there's hardly any, there's no need of a residual here, so we can just take the residual out, and then we don't need the cross-classified modeling, which you can just do this as part of the two-level modeling. So, we have this, the intercept is regressed on the logarithm of t, and then because that was a random slope for x, we actually have to multiply the time multiplied by the covariate. And those, so this x2 now is the linear trend multiplied by the covariate, because that was the slope on x. And again, the quadratic term multiplied by the covariate. So you can just estimate this essentially now as a two-level model. There's no need. You can estimate. You can estimate it also as a cross-classified model simply by fixing these residuals for y and s to 0 here, or to small values or something like that. But you don't need to. You can also just estimate it as a two-level model using the. You can add the parametric shapes inside the model in a two-level model when you don't have time-specific residuals, time-specific random effects with greater than 0 variances. And that's that. I think we'll leave the last little bit.
Perfect. Perfect timing. All right. Thank you, Tiamer.
Yeah.
Now, I'd like to throw us off kilter a little bit. Can we have some audience participation, maybe? Who is ready to ask Tiamer a question?
In the save factor score option, is there option of getting the factor score for the last 200 iteration plausible value instead of the summary of the factor score?
Yes, yeah. So this is with the command factor score is equals all. Yeah, you add that command, and then you get a little plus sign, to each factor score variable to indicate that there's imputed actual values. So the full distribution of the factors isn't there. So keep in mind we're kind of struggling at this point because there's so many random effects. So we're a little bit struggling with saving these factor score files. They become quite large, and we're saving them as text files, and then we're saving this to the graphics files. So just beware that what happens is, well, I'll actually just demonstrate that. So here's what it was quite upsetting actually to see that this actually what is that? So here is this file, which of course I didn't want to run because it takes long. Okay, so here's the we are actually asking to for the factor scores here. So here's how the run goes. We have this. You saw the first few iterations. Let me just go back up here. So you got the 200 iterations, right? That was the convergence. The model was already estimated, everything was done. So now we're going down, generating imputations, and those are the factor scores, 200 factor scores that I asked for. And it keeps going, but fairly fast, right? Then, bam, nothing is going on. So what it says here, writing factor score, plausible values to save data file. So this is just the actual writing of the file. There's no statistics here. It's just the basic thing. It's kind of annoying that we got to the point that we have to deal with that issue. And we have some, we're trying to make this process also better for the next version because, it just, it takes a long time now just to write the file. So still writing that file.
Just to add to this, for those of you who don't know what plausible values are, so the idea is we want a factor score value for each person. So if you consider one person, you get not only an estimate of that person's factor value, and not only a standard deviation or standard error for it, but you get the whole distribution for one person's factor score. So that's the plausible value distribution that we're talking about here. So you get much more information on the person level than you do otherwise.
So yeah, we'll wait until it ends up writing the file. But yeah, we will make it better. So we have some ideas to make that faster.
This is very conceptual. I have a feeling I might be pushing this a little bit, but we often are trying to study two individuals interacting over time. And so one interest is, can we plot and analyze? When you said time varying, I'm in my mind imagining two timelines coming together and going apart over time, and whether or not we can get to a point where we can estimate two individuals affecting each other in this way.
So this is I would say that this is the VAR vector autoregressive model. So and we really, I think we're kind of trying to see where we are, and I think that the potential of this model is huge. Because this is the only place where time really makes the direction of the arrows to go only from left to right. You cannot argue that this is a correlation. It goes in the way we want. We want causation, and that's what Ellen has also been writing about. And I think that this is a great potential to actually really establish causation between variables. Just monitor them through time, and get these errors estimated, and yeah. But yeah, that this is a great model. Yeah, the VAR1 model.
You mentioned about choosing the time interval and introducing missing data into the data set. How does that work out if you have measurement burst design where you have closely spaced data followed by substantial gaps and then closely spaced data again?
So there's two ways, I guess. There's different ways, I think, to deal with that, and I would say that almost all the autoregressive effects actually they kind of disappear. So instead of actually having 5,000 missing data points between the bursts, you can essentially shrink that to 10, so that you don't have to do this, and you essentially get the same model because the time connection between the bursts is going to disappear anyway between 10 periods. So that's kind of like the pure, kind of a knee-jerk reaction that I would have on that. But then you can also consider having to actually modeling them as the last topic I was going to show in the afternoon is just maybe you can deal with that either as a 3-level model. You can also deal with what Ellen was doing yesterday, where you put the second burst as a second variable. It kind of depends on what you really want in the model, but I would say that keep this in mind. Don't put like 5,000 missing data points between the bursts, because it makes no sense. It's just gonna kill the convergence and not contribute anything. Yeah, because we impute every single one of these points. So
I have a question about slide 21. So this is the design where they had 5 measurement points that were randomly signaled throughout the day. And then it looks like T is 24 in this example. So my
slide 25, did you say?
21.
Yeah.
So T is 24. So I was just wondering if I have an interval contingent design and like all of my times are between 10 a.m. and 9 p.m. Is that okay to use this hour design if I have no observations between 9 a.m. at the end of the day and 7 a.m. at the beginning of the next day? Does that make sense?
I mean, I would say that it's okay, but you have to keep in mind, I'm not sure if I understand the design. So where do you have a certain period of time where there's no...
During the night.
During the night, they have no...
So again, I would say that one option is to actually model within the autocorrelation and then between the autocorrelation. That would be one way to deal with this. I would, I've been kind of tossing stuff around when I was trying to convince, Bengt and Ellen that maybe we should actually do the kind of have a shrinkage period. So the night hours, maybe they need to be estimated as not be taken as an actual time, but it should be reduced. Of course, you depend on the application. I don't know.
Would you say that there is a correlation between the 9 p.m. and the 7 a.m. outcomes?
I'm thinking like recovery from work is what we typically study. So, you could say if you're less recovered in the night, there'd be an autocorrelation with the following morning recovery.
And it would depend on the distance between that last time point in the evening and then in the morning?
If you sleep more, maybe,
Yeah. So, keep in mind you can increase the time interval to 2 hours. So if you increase it to 2 hours, then you have less missing data, and then this, night time will be only 4 time points that have missing values. So as long as you don't have too much missing data, that you should be able to estimate it on the raw scale. But again, I'm not really, sure that the nighttime should really be the same equivalence as the daytime. So.
So you're saying shrink the 8 hours of nighttime down to maybe 2 hours?
But I'm like a mathematician, so don't take, so I don't know.
Well, I guess my question is, I think this could really help me because my T would be I thought it was only the number of measurement periods I had, but if my T can be 24 instead of 5, that will really help me use this. So.
Right. So this will help, kind of actually have the correct distances between the times of observations. Yeah.
I have a question. Could you and Ellen say something about the relationship between the version 8 approach to time, which is sort of a discrete time approach, compared to the continuous time approach, and possible translations between the two?
In terms of estimation, it's I don't think that it's that much more difficult than this.
So just as a background, there's a literature on continuous time series analysis. Do you want to say something about that, Ellen? No?
We are working on a number of papers on this. One paper actually where we are looking at this idea of adding missing values and choosing different kinds of grid sizes when you have ESM kind of data where the intervals differ. And basically the papers show that if you choose a finer grid, your results become more and more like the results you get when you would do the actual continuous time model. And that's exactly what you would expect, based on your intuition. But it's nice that the simulation results are supporting this intuition. But yeah, it will probably be a little while before the papers come out.
Great, thanks.